Hi. Um, First of all, I know it's time to eat, and for this reason, thanks for coming. It's good to know people who have hungry for knowledge, okay? And I'm going to introduce myself, okay? I'm Rubén Martínez, and I have worked as a security pen tester, as an ethical hacker for 11 years. But now I'm working data hack, doing research about how to integrate deep learning with robotics, okay? And what's the topic of this talk? Well, I'm going to show you how an attacker could use reinforcement learning to evade the static analysis engine used in antivirus software, okay? Is there anyone who has ever worked on malware analysis here? No? Okay, perfect. Well, static analysis includes or consists of gathering information about a binary file without running the code, okay? And static properties could be the strings embedded into the file, or header details, or metadata such as the creation date of the file, of the packer signatures. And this research is focused on attacking the static analysis of Windows PE files, okay? And what's the meaning of PE? Well, the meaning of PE is portable executable. It's a file format for executables, for object code, for DLLs, libraries, used in 32-bit and 64-bit versions of Windows operating systems. And in this picture, we can see the structure of the PE file format. And a section to be highlighted is the import address table, which is used as a lookup table when the application is calling a function in a different module, or the export address table, which contains all functions exported from DLLs or libraries, okay, as introduction. Okay. But, okay. Now, I'm going to focus in the key of this talk, reinforcement learning. Reinforcement learning is the task of learning what actions to take given some situation or environment. This is the word, environment, so that the agent, who is the learner, okay, has to maximize some kind of reward, okay? And how does it work? Well, at each time step t, the agent receives an state st and selects an action at from some set of possible actions, okay? And in return, the agent receives the next state st plus 1 and a scalar reward rt, okay? And the agent uses a policy pi, okay, to choose the next action, the next movement, okay? There is a problem with immediate rewards because a good current reward doesn't guarantee good future rewards. And because of that, the goal of the agent should maximize the maximum long-term reward from each state st. This is the goal of the agent. Now, we are going to see a very important concept related with reinforcement learning, the optimal Q-value. We can define the optimal Q-value as the maximum long-term reward for the action AT on the state ST, okay? And here we can see the formula. RT, in this case RT, is the best current reward plus the gamma parameter, which is now discount factor, which means that the reward times 10, for example, is weighted a little less than the reward at time step 1. And this gamma parameter takes values between 0 and 1, okay? And multiplied by this part, the maximum long-term reward at time step t plus 1, okay? What we are going to do now is to approximate, this Q function rather than iterating over all the actions for all the states. And the next thing we need to do that is a neural network which will approximate this neural network for us because we are lazy and we are going to use that tool, okay? Next, we have to look at the loss function that we are going to use to update that neural network using gradient descent, okay? And this is the formula. And this formula can also be written as observed reward minus target rewards in brackets to the power of 2. And in this picture, we can see how to code this formula using TensorFlow. We can see how to get the observed reward and the target reward, okay? And now we are going to see the reinforcement learning technique which is used in the proof of concept of this talk, which is known as actor critic. Well, actor critic algorithms, or the actor critic algorithm is used to represent the policy function independently of the value function. And the actor, or the policy function, is known as the actor, and the value function is referred to as the critic. And the actor produces an action given the current state of the environment, and the critic produces a temporal difference error signal given the state and the generated reward, okay? And what is a temporal difference error signal? Okay, pues it's only the error in the estimate made at that time, okay? We are going to use, in our proof of concept, neural networks to represent the actor and critic structures. And as a final tip, you are going to hate me because of these formulas. In our proof of concept, we have to say that we are going to update the weights of the neural network of the actor, okay, using the gradient of the output, using the gradient of the output of the critic network, this part, multiplied by the gradient of the output of the actor network, overrated by a mini batch. And this is how we are going to update the neural network of the actor neural network, okay? Summarizing, we can say that the output of the critic networks drives learning in both actor and critic network, okay? In both actor and critic structures. And to finish the talk, because we only have 10 minutes, in the context of malware evasion, our environment will be or consists of a malware sample. We are going to use one malware sample per game, in our case, okay? And a customizable antivirus engine, okay? And in our proof of concept, this antivirus engine will be a gradient-boosted decision tree model trying on malware embedding samples. And our proof of concept will use a library called Leaf, which means library to instrument executables formats, and it allows our agent to modify the binary on the fly, okay? And we are going to represent the environment using a feature vector of this dimensionality, composed of the following general categories of features. The P header metadata, as we see before, the section metadata, import and export table metadata, counts of human readable strings like URLs, file paths, and registry key names, and byte histogram, okay? And next, the agent will be the algorithm used to modify the environment, I mean the malware sample, okay? And in our case, at each step, the agent receives the next following feedback. Receives a float reward if the modified malware sample has evaded the antivirus engine, then the agent will receive a reward of 10.0 or 0.0 otherwise, okay? And a feature vector summarizing the composition of the modified malware sample, okay? And a Boolean value indicating if the environment, the malware sample, needs to be reset. If this value is true, then the episode was successful, okay? We got a malware sample which isn't detected by the antivirus engine, okay? And based on that feedback, our agent has to choose one action from subset of possible mutations. And this is very important. These actions doesn't break the code execution and the structure of the P file format of the malware sample, okay? And because of that, we have a small number of possible actions that can be made to the P file format of the malware sample. And here, we can see the actions used by your proof of concept, okay? And note that most of these actions are stochastic. For example, when renaming the section name of a malware sample, the new section name is chosen uniformly from a set of sections names found in Benin files, or the compression level used by the packer is chosen at random, okay? And to finish the talk, it's time to show the demo effect, the moment that you have been waiting for. And I have trained a reinforcement learning model, trained on malware samples that I have created using Metasploit. Do you know Metasploit? Anyone? Well, Metasploit is a popular framework in the security world used to develop exploits and malware samples, okay? And we are going to use the trained model to make the test set of malicious files undetectable to the antivirus software, okay? In this case, a gradient boosted decision tree model. And now we are going to see the demo. Here, I'm launching the Inference script, okay? And now, we are going to see how the trained model is choosing the best modifications, the best mutations to make each malware sample of the test file undetectable to the antivirus software, okay? He's trying to choose the best movement, the best movements, the best modifications, the best actions, okay? And finally, we are going to see, in this case, we are going to see the output. This file here is a malware sample which has suffered this list or this sequence of modifications, of mutations. And before of that modifications, this malware sample was detected as viruses, a virus in this case. We can see here in a few moments. We can see how the label of this malware sample before of this modification was 1.0. It was detected as malware. And after that modifications, after that sequence of modifications, we can see how our modified malware sample has evaded, in this case with label 0.0, has evaded the antivirus engine. And this is another technique that we can use to make more robust the antivirus engine, using these outputs to harden the antivirus engine, okay? And I have finished the talk because I only have 10 minutes. Thanks again for coming. If you have any question or if you are working in any topic related with reinforcement learning or deep learning in general or in robotics, we'll consult later, or if you have any question now. Yep. Oh, sorry. Okay, well, thanks for coming again.